what are these things, what's emerging, why do I care? So for those of you that don't know me, if we're just now meeting, so my name's Greer. I like to teach about packets and talk about this kind of stuff to people, audiences all over the world. I've been at SharkFest as an instructor for, I think this is my 13th one. So I started back in 2011, and if you had been at the 2011 SharkFest, it was in, I want to say that was in Berkeley. I would have been over there hiding in a corner, terrified, hoping no one saw me, because I definitely was the dumbest guy in the room. I still feel that way when I come to SharkFest. So if you ever feel that way, if you're like, whoa, this is over my head, whoa, I'm never gonna get this, man, I've got the dumbest question I don't wanna ask because everyone else is way more advanced than me. I don't wanna slow the course down because everyone else is understanding this. I'm looking at all these lines, everyone around me is ripping and just doing the right thing with the right filters except for me. If you feel that way, if any of those statements are true for you, you're looking at somebody who has definitely felt that way. I still do. I still have imposter syndrome at SharkFest, okay? So let's just get that out of the way. You belong here, and you can do this, and we're gonna take on a tough subject here. That said, let me tell you what I am not. So I'm a packet person. I like to talk about packets. I like to help my clients troubleshoot things and get to the root of different problems. One thing I'm not is a DNS architect. So I have never been on site with a company and had to completely engineer and implement an entire DNS system. I've had to troubleshoot it. I've had help them figure out what was wrong. And I've seen these trends over the years. And so hopefully that gives you a bit of what I am and what I am not. So this is not going to be a three-fin, super advanced, ultra deep dive into the nuances of how all of these things work, because frankly, I just don't have the time. I was just talking to some of the gentlemen up here in the front row, and I actually would love to turn this topic into a full one-day pre-conference class next year. I think that would be kind of cool if I could. Sometimes when I take a course, I heard another instructor say this one time. When you're covering a topic, think about jet skiing over something, snorkeling and seeing what's beneath, or scuba diving, right? If you're scuba diving, you're going down deep under the water and you're looking at every little thing and you can see it up and close, but you're not going to be able to cover a whole lot of ground, right? Because you're up there, you're in the weeds. Same thing with a snorkel. You're a little bit more distant from it, and then jet ski, you're just blowing through. So I'm in this class for the next hour, we're going to be right between jet ski and snorkel. But that doesn't mean we can't sidebar afterward. And even if you keep watching my YouTube channel, I've been popping this kind of topic stuff out there, and I'm going to continue to do so the more that I learn along with you, okay? So just want to put that out there. Again, welcome to class. Excited to have you all here, or welcome to the session, I should say. Talked a little bit about myself. So I'm the executive packet head at Packet Pioneer. That's my name. That's my game. I like to do packet stuff, and I'm excited to meet all of you. I mentioned that at the start, bit.ly/SFUS26_DNS. Did anybody pull that down successfully yet? Did that link work? Yeah, got some thumbs, cool, okay. If not, it's about a 2 meg file. You've got about 6 or 7 packet captures in there. We're just gonna see how far we can go, okay? Also, a bit of a rule that I have in all the sessions that I teach, be nice people. If someone asks a question that seems simple, we're going to let them ask that question. I was just talking to several of you beforehand. Some of you are brand new to DNS, brand new. Some of you have a bit more experience as network engineers. Some of you have even more than that. You're tasked with rolling these systems out on networks. So we've got a gamut of experience. So I'm going to try to play to the median here, okay? All right. Now what we're going to cover here in this session. So first, we're going to talk about DNS as a service and why it's so important, but also some of the challenges that there have been in the last, well, ever since it was incepted, to secure it. So DNS, actually, I should ask you, how important is DNS? What do you think? Someone give me a very simple description of what DNS does. Let's just get that out of the way too. What is it? What have you heard it called before? Phone book of the internet. Why do we call it that? You got a name you want a number. Nice. Or a number you want a name. Good. What else? Go ahead, Tony.
What's a phone book, Grandpa?
Well, son, in my day. Right. Yeah, that's a good question. So, I think just very simply with DNS, I pull my phone out of my pocket. I don't dial my wife's phone number. I would be challenged to do that, which is probably a bad thing. To remember what that is. I just call wifey, and she picks up the phone. So DNS principally is connecting those two pieces of information. We live in a name and domain world, right? We like names, wireshark.org. We're not going to punch in an IP address. Lots of reasons for that. That address might move. It might be something else the next time. CDNs, content delivery networks, so load balancing across systems. So DNS, very important. It's funny, when at the start of my career, I noticed that everybody was blaming the network if there was a problem, something slow, and, oh man, it's the network. People have heard that before? Oh, it's a crappy network. And then people started going, oh, it's the firewalls. And now more and more I'm hearing, that's why I made this shirt. It was DNS, okay? So it also can be blamed for the things that might go wrong in a network system. And that's just because it's so stinking critical. It's a very important piece of the puzzle of bringing an application to your browser or to whatever it is you might be using it for. Now, it's a simple protocol, but it also has been a challenge to secure. That's what we're going to focus on today. So we're going to talk about these, the acronym SOUP that you might see around DNS, so DNSSEC, DoT, DoH, even DoQ, and what they look like on the wire and why we need them. Part of where this session came from is last year at SharkFest, we were doing, in the pre-conference class, we were doing some of the DNS piece, and we were talking about the security of DNS. And there was a lot of confusion about what those things were. With just being honest, someone was just like, oh, I think DNSSEC secures things, right? That's what it means, right? It's security. Or DoT, what's the advantage of DoT? Do you need both? Like, do you need DoH and DNSSEC? Do those conflict? Where do those live? What is all this alphabet soup? So those questions started coming in that session, and then I thought, you know what? It's time to just take a few minutes and unpack some of those, okay? Now, before we get too deep into the weeds in the security part, why plain text DNS is a problem? So let's first talk about DNS as it exists today. First, and we'll just do a quick flyover here. So if I just am a standard resolver, I'm a client, I send a request to my DNS server, I'm asking for a certain type of record. That record can be a lot of different things. I could ask for an IPv4 address. I could ask for an IPv6 address. I could ask for a canonical name, an alias for a server. Like, are you also called this? I might have your IP address, but I want your name. It could be that I need, if I'm migrating something to a different system, I want a text file. So there's a lot of different messages that can be exchanged within DNS. But all of that, if you capture it just off the wire, it's wide open. The request and the response, it's all there for the world to see. What's wrong with that? Why do we care? What's the concern? Is there a concern? Can we just keep going like this? Go ahead. Know where you're going, that's true. If you can passively listen to people. Any other concerns on that? It can be forged, yes. It's an interesting, we'll talk about that in just a minute when we get into our first PCAP. Like, what's the validation for what I'm getting back? How do I know where that came from and if this is true? If I go to wireshark.org, how can I be confident that the response is actually wireshark.org and not wiresnark.org, somewhere else? All right, so that's part of what the challenge is. So Let's go ahead and just do a quick, this is just a standard DNS 101 speed run. On your end, if you would, one of the first labs, let me just fact check myself. Okay, if you bring up the DNS full recursion PCAP, you can pull that up and then you can start pawing through that as I run through this. So, speed run with standard DNS. So DNS is a big deal, right? The world relies on it. But there's no one place, one server in the world that knows all IPs and all domains. There's not one box you can go to that knows everything. And there's reasons for that. Think about how large that system would be. Think about how often it would need to be updated if I just went to one system, one box, one database. And imagine if the whole world was talking to that one database. It wasn't distributed. It wasn't being updated. So with DNS, in order to make it reliable, make it scalable, make it quick to update, it's a hierarchical protocol. What does that mean? Well, basically this runs us through the steps. So if I'm a client, and I think, you know what, this slide is a little wordy on me. I like to just show it this way. If I'm a client, I'm also known as, you might hear the expression, stub resolver. So I'm the one doing that request, and I'm sending it out to my local server. So let's just say my user upstairs types in example.com. That's what they want to resolve. I send that to my recursive name server or that caching name server there. Now, on your system, it really just depends on how DNS is set up for you. It could be that this system, let's just say it's your home network. It could be that this system is your local gateway, your local router, that's forwarding to a known DNS resolver in your ISP. It could be that's the case. Could be that this is a server that's sitting on your enterprise environment, and it itself is able to do some resolution. Whatever it doesn't know how to do, it does the rest of this recursive lookup. But let's just say, okay, that recursive name server has no cache. It just woke up from a nap and hopefully wasn't sleeping too long. But this client wants to resolve example.com. There's 3 steps on the back end that this resolver has to take in order to resolve this address. Now, the thing to remember with DNS names is you actually read them backwards. You don't read them left to right. You actually read them right to left. So the first thing that we got to figure out is, so where is example.com and what is the most recent IP address for this server? Where am I going to go and send this user? The first thing we do is we go and we talk to what's called a root name server. So we send that full request, example.com. You notice there's a little dot at the end just to the right of com on our request. So that means, hey, go to root and see what root has to say. So that resolver already knows, it's got a baked-in list of what those root servers are. There's 13 names that it could look up. You're going to see that in that recursive PCAP in just a second. So our resolver is aware of the root servers. So it goes, hey, root server, talk to me. What do you know about this domain? Root server comes back and says, you know, example.com, that's kind of a long name. I don't know what the world, I can't resolve the world here, but I do know some of my buddies, they know what .com is. So let me redirect you over to the com top-level domain servers, and they can take you to the next step. Okay, so root, it just takes you to the top-level domain that's coming next. So you think about what's at the end of a DNS name. It could be .org, .net, .whatever, .chris. The root's job is just to get you to the top-level domain of whatever that last part of your domain lookup is. Roots don't know everything. They just know who's responsible at present for the last part of that domain name, okay? That's one myth busted. Sometimes I hear, oh, roots know everything. They don't. They just know that final part. So root comes back and says, you know, that's not me. I don't actually have that record. In order to get to the real brass tacks, you got to go talk to the top-level domain, the TLD for com. So the resolver says, great. I'm going to go to the TLD for com. So it could be that I actually have to ironically do a DNS lookup to resolve the name for .com, but let's just say we go straight to that com server, that TLD that the root told us to talk to, hey, talk to me about example.com. What do you know? TLD comes back and says, you know what? I'm not the actual domain authority for example.com. I don't have the latest, greatest on that, but I know who is. I know who has the latest lookup and is the domain authority for example.com. That's called an authoritative name server. So what I'm going to do is I'm going to say, hey, let's go talk to the authoritative name server for that domain. That's going to be the one that actually has got the goods. It's got the latest, it's got the greatest, it gets updated. It's constantly being refreshed. It's up to the second. Go talk to that thing, or even fraction of a second. I go to example.com to that authoritative name server, and then that's where I finally get my reply coming back. That's the IP address that I wanted. Then my resolver can send that back to my client. So from a packet perspective, just for most of us for day-to-day driving with Wireshark, you don't typically see that back end too much unless you're living in that space. Anybody agree with that? I mean, do you spend much time on that back end piece? Seeing a few head shakes, right? A lot of us, we live on this side. We're on the client end, right? We see a request and we see a response come back. And then the rest is all this magic stuff that happens on the back end. So one of the reasons why, I'm just going to keep the flyover here on the speed run. One of the reasons why I wanted to give you that full recursive lookup is because, man, that's a tough thing to capture. Unless you have access to those systems in like a real environment. So actually, Infoblox, of all people, they work with me to get some of the PCAPs together for this, and they just said, hey, give it, share it, use it. But what you'll see in that packet capture is every step in this chain. You see a client, you see it go to a root, you see it go to a TLD, you see it go to the name server, and then finally we get that response back. Now because of this, just because of time, I wanted to be able to give you guys a lab and have you go through all those pieces, but what I'm going to do is just bring that up really quickly on my machine, walk you through it, and then we're going to talk about how this is secured. Just wanted to be sure everybody was clear first how DNS works, okay? All right, let's go ahead and open up that DNS full recursive packet capture. And like I said, I'm going to have to calm my excitement, because I love this stuff. All right, full recursion. Okay. Boy, I don't even know what I was doing before this. There we go. Okay. Okay, so first, something that you can see, if you go to packet number 1, and I'm just going to zoom. All right. So this is our client sending to its resolver. This is the address or the server, the DNS server that it got from DHCP likely. You see in packet 1, you got that arrow for 1, and that means that this is a DNS request. Okay. So this was the request. Now, since the Wireshark dissector can read that thing, Wireshark can connect the request to the response. So go ahead and see, if you take a look at that dotted line that goes down the left of the side there, where do you see the other arrow? Do you see the response come back? See that down at the bottom? I think it's like frame number, what do you see? 31? I'm just too lazy to go look. Right, so you see that that's actually the client request that you saw on the previous slide. Then all this stuff on the back end, and then the final response coming back. And it's all in nice, clear text. Now, when you see the request, you're going to see that as you click down these. So first, we're going to our destination. Now, on the back end, you start to see this resolver, a 0.140. On this interface, it's using an IPv4 address to talk to the client. But then as soon as it goes to the back end, it goes to IPv6. Interesting to note, totally fine, totally legal. If you click on packet 2, check out the response is in packet 5. So let's take a look at that real quick. I want to just unpack this just a bit. I'm going to remove this sign to live just because, okay, there we go. All right, so we send this request. Now let's actually take a little closer look at this request. I'm on packet 2, everybody. And I'm going to expand, whoa, boy, okay, calm down, Chris. All right, so DNS, if I come down here to flags, just to fly through here, this is on the request packet 2, so this is a query. Recursion was desired on the previous packet. I don't have to do that now because I'm actually on that back end. Yeah, there's one question here. Let's dig in and see what that question is. Here's a query. Infoblocks.com, I want an A record, which means I want an IPv4 host address. If I come down here to additional records, there's this extension down here where I'm sending more information to that server. One thing that's interesting is UDP payload size. What that means is, hey server, my datagram size limit in DNS is 512. That's what this request is alerting that server to. Server goes, great. If I can get everything back to you in 512 bytes, thumbs up, I'll send it back. However, if you got to go bigger than 512, I'm going to have to take a separate action here. So let's actually see what happens in packet 5. Packet 5 comes back. So here's our response coming back for that address. So here's infoblocks.com, additional records, in this record coming back, we see that this is not an actual answer to my question. In fact, if you look, there's no answer resource records here. It's interesting, in a DNS request, you're going to see the questions and number of questions that are sent to a server. You can have multiple questions go to a server over a single UDP request or a DNS packet. A DNS request, I can send several different requests to a server. And you're always going to see that here. The responses, though, back from the server, you're going to see answer resource records, authority resource records, additional resource records. So that server came back and said, hey, bud, this is not an answer, but I do have a record that's probably going to be something you want to look at. Yeah, the UDP payload size that I can do is 1232, but check this out. If I go to message is truncated, you see this bit right here? This means a lot when it comes to UDP and TCP. Basically, the server's saying, yeah, that 512 that you wanted, I have more to say than can fit in that single 512. I'm going to have to go ahead and open up a TCP connection. So go to packet 6. This is the same IP conversation, or IPv6 conversation. You can see that 6 and 2, they're going to having the same conversation. But you notice here, our protocol changed. This is a TCP SYN. Wait a second, I thought DNS was only over UDP. That's not true. Larger conversations, it will fall back to TCP. You just saw why. We asked a question, and the answer is bigger than 512. Now, in some cases, it can be larger than 512, but let's just go with that for now, because it's on the thing. This is where you're seeing it fall back to TCP. Now, so for a larger amount of data coming across. Now, this is one thing that I've seen in my clients. So what happens if they block TCP 53? Because DNS is UDP only. What did I just do? I messed it all up, right? This is going to break, it's going to break this part of the conversation. Some things, yeah. So it's going to break this piece, yeah? So sometimes that's something I'll listen for with my customers. If they're saying, okay, some requests are coming back, some aren't. That's something I suspect. Like, are you blocking TCP by chance? You'd be surprised at how often there's a yes there. Okay, I'm just going to keep flying through everybody. So we go to this DoD box, and I'm just going to do a right-click conversation filter, TCP. And you can see we do a SYN-SYNAC ACK, just standard boilerplate TCP. We do a request, we get a response. This is for a name server for root. I'm going to go ahead and remove my filter here. And actually, that's not the one I want to look at. I want to look at right here, packet 15. I'm sorry, I lied, packet 19. You see this one that has, on my profile here, I have a payload size, which on a sidebar, if you're interested in seeing how to add that, I can show you. Just go down to packet number 19. We're going to right click. We're going to do conversation filter. We're going to do TCP for right now. And in here, so we send our standard query, b2b infoblocks.com. That's what we want to resolve. The server comes back in packet 19, And if we just scroll on down, check it out. So this is not yet an answer resource record. Root is saying, I don't know, but I know who knows. So the authority resource records down here, these are the authoritative name servers for, you see that GTLD, so top-level domain, top-level domain.servers.net. Those are the guys you probably want to go talk to. I'm not just going to tell you, wait, there's more. I'm not going to just tell you their names. I'm also going to tell you what their IP addresses are down in the additional records. So you don't have to go resolve the name of a DNS server. That's kind of like more work than I want you to have to do. All right, so root comes back. I don't know the answer, but these guys do. Go talk to them. I say, cool, okay. I'm going to remove my filter, and I'm just going to take another little walk down here because I'm interested. And I'm going to go to, let's see, standard query. The next one, packet 21. Let me just take a little walk down here. Okay, so this is ::30. So this is actually one of the, if you dig through, you're going to see this was one of the TLD servers that the root responded with. And if we take a look at that one, packet 21 is the request. We're talking to Infoblocks, that's what we want to resolve. It comes back and says, whoops, 512, but here's the request. If you take a look at packet 23, this is an actual response saying, you know what, all I know is about this top-level domain for .com, but I don't know the actual domain. I'm not the authoritative name server, the guy that really, really knows. You're going to have to go to these authoritative name servers, infoblocks.com. Name server 5, name server 6, name server 7, name server 1. And if you scroll down, by the way, we're coming back to what this all means. If you go down to additional records, that's where we actually get the addresses that we can go talk to for those servers. And then finally, this is where things really get fun. I'm going to come down to my final request, and that is right here. Look at packet 24. This is the final name server request, and boy, that's a big IP address, IPv6. So we finally send that request over, and it's going to be exactly the same thing, like fine, just who's B2B, Infoblocks.com. You're the Infoblocks name server. Hopefully you know. And then it comes back in packet 30. You can see those that 24 and 30 are connected. 30 comes back and says, look at the payload size 413. We're still under that TCP ceiling that we need to use. We come down here, and then, finally, we have an address come back, 8.39.143.138. And it's also, interestingly enough, it's got this resource record signature. So I'm just building to that in just a moment. But, so this is our final answer that we wanted. We finally got our answer resource record. We got an address. And then finally, you're going to see at the bottom, the resolver takes that address and kicks it back finally to our end user who's been sitting there waiting, and now it has that address come back. So thankfully, as an analyst, oh yeah, go ahead.
If I'm getting authoritative name servers back, and let's kind of say like here in the example with like between 6 and 10, how does my computer make the, how does the resolver make the decision on which one? Do I try the first one, give it a couple seconds, if I not get something back, I go for the next one?
You are exactly right. I've seen most resolvers, most of the time, pick the first one. Yep. Unless they have something in cache. And you also notice too, if you take a look at the resolver, like when it goes to root, you also notice the order of those names change. Like it kind of self-load balances, which is interesting to watch. Great question though, and thank you. All right, I just did a fly through. Now, you have this packet capture. I invite you to literally line by line dig through. It's a fun thing. This is your basic DNS resolution, but a couple things you just noticed. All of it was in clear text. None of this was decrypted. The other thing about it, though, is if I'm that end user, let's go down to the bottom. Let's right-click on, here we go. Let's come down to the very bottom. I'm on packet 31. I'm going to right-click that guy, and I'm going to say conversation filter UDP. Okay. So request response. This is just a nice filtered example of a request response. Now, question for you, I send out this request, I send that out to my resolver, and I get this response come back. But what am I, just for standard DNS, what do you think my resolver not talking about any of the security methods yet, or rather my client, how does it know that that response really was the right response to get back? How does it match a request to a response? What do you think? It's actually really simple, everybody. Transaction ID. You see up on the top there? That's exactly it. Transaction ID 2380. So I send out 2380. I have that as a transaction ID in the request. And when a transaction ID that matches it comes back as a response, I go, cool, transaction ID, this must be what I was asking for. That's it? A 2-byte transaction ID? It's a lot of trust. Do you think that's hard to spoof? It wasn't designed for security, like so much wasn't. Exactly. Neither was TCP. Yeah. Get it working. Oh, and I love with DNS. Don't just do IPs. Now could you do all these messages, and can you have all these text records, and could you do all this other stuff too? Okay. All you do to resolve or to match a request to a reply, seriously, people, it's that transaction ID. That's enough for DNS, generally speaking, most of the time. That's a problem, right? In walks DNSSEC. And we're going to talk about that. Let me get to my little slide that shows us where we're at. Okay, so when it comes to, you just saw a few things on the wire, very intentionally. I wanted to walk you through that. Sorry, I had to do my flyover. But two different problems we have. One is confidentiality. So who sees those queries? If you go to a coffee shop or you're in an open network somewhere, or even right here in this hotel, it's very easy to inspect those queries. I know right what you're going to, okay? And I can see the responses. Now, confidentiality, this note here on my slide, solved by DoT, DoH, DoQ. So DNS over TLS, DNS over HTTPS, DNS over QUIC. Those terms are there to protect your confidentiality. Now a passive listener can't just listen to your DNS requests and responses. It's encrypted, okay? That's one part of securing DNS. The other, integrity and authenticity. So who can fake the answers? How do I know that this answer came from the machine that I think it should be coming from? How has it been signed? How is it validated? That's DNSSEC. All right? So if you think in your brain, this is just what I had to do as I was learning this stuff. So this piece of the puzzle right now, here in time, this is growing into the back end, but for right now, between our resolver, or between our client and our resolver, that's where DoT, DoH, DoQ live. That's their sweet spot today. That means a passive listener can't listen in on your DNS. That's the intent. The DNSSEC is there to protect the cache of the resolver. It's there to protect the cache of the resolver. DNSSEC doesn't encrypt anything. You just saw DNSSEC in a packet. It was wide open. It was that record signature, that field we flew over. We're going to come back to it. It's right there. You saw it. But that's DNSSEC at work. It's signing and authenticating that this thing is what you think it is, and it came from the right place. Now, why would we need that? Well, that's because attackers can change stuff. You can send out a request, and you can get a response from somebody else, because again, all we watch is what? The transaction ID. If I send a request to what I think to be an authoritative name server, and I get a response back that says, no, go over here. Or worse, I can poison the cache of that resolver. If that system, if that box is, look at all the systems that just pass DNS through as a resolver, depending on the protections that are built in there, protecting that cache internally, I need a mechanism to validate that the information I got is good and I can trust it. That's what DNSSEC is all about. Okay? So right now, if you take nothing else away from this session, securing the actual communication and encrypting it, DoT, DoH, DoQ. Protecting the cache of a resolver or even validating it for yourself, DNSSEC. Okay? I'm just going to let that hang for a minute. So does DNSSEC encrypt? No. It's not designed for that, which is kind of interesting on the name, right? Like DNSSEC, DNS secure, it's secure DNS. Oh, I can't read it. Yeah, you can. You can read it right off the wire. Okay? So maybe we could have rethought that name. Anyway, but DoT, DoH, DoQ. All right, so that's why we need it. We want to protect our cache on our recursive name server and validate where that thing came from. So let's go ahead and take a look at this in a packet capture. Go ahead and bring up the next example that I have for you. DNS, we're going to take a look at DNSSEC failed simple. You have two requests that are in there. One that worked, or one that did not work, and then one that did work. I'm going to give you a few seconds to take a look at those DNS packets, just to give yourself a moment to let your eyes do some of the work. What I want you to notice is in the second DNS transaction, if you see a request, you're going to see a response come back with that signature in the response. And that's DNSSEC in action, okay? I'm literally going to give you like 2 minutes to take a look at that thing, okay? And then we'll keep moving. So for me, when I started coming to the SharkFest, I would, a presenter would be up here and throw a packet capture at me and just start ripping through it right away. And I'm like, can I just have a quick second to get my head around this thing? Who's the client? Who's the server? What's the network round trip time? So I'll just give you just a minute. Okay. You know how you can capture a DNSSEC failed message? Go to dnssec-fail.org. All right. Let's just step through this then. Let's just take a look at one that failed and one that didn't. So our client, 1054, it's talking to 1111. And if we take a look down in our DNS, so there's a few little things we want to check out. So authenticate bit is set. So our recursion, this is another one, recursion desired. So the client can say, hey, recursive server, I want you to go do your backend recursive thing. I'm client, I want you to go do that. So that's what that bit is for. Woo, boy, I keep leaning over. Sorry, everybody. Okay, questions. Let's go ahead and take a look at the query that I'm asking for, dnssec-fail.org. I just want a standard host address. So just give me your v4 address. Take a look at this UDP payload size. So if the underlying network can handle it and I can do larger packets, I can handle up to 4096 as a UDP payload. The MTU will probably get in the way of that and not allow that to happen, but the client is advertising that that's possible. If you go down to the end of the additional record, you see this, the DO bit accepts DNS security resource records. So right now what I'm telling my resolver is, hey, I'd actually like to see a DNSSEC record come back with whatever it is. I want you to go ahead and send a key back with it so I can validate where it came from. Let's take a look at the response. So response comes back, and right up in the flags, I can see there's a server failure. So something went wrong. Let's go find it. If we say, here's our question, it's going to copy that question or repeat that question back to me. Hey, Chris, this is what you wanted. Here's your name. Here's the type that you wanted. Here's the class. And here's my additional resource record. If you go down into additional records down at the bottom, you're going to see extended DNS error. So whoops, bad. DNS key is missing. So we had no DNSSEC record that I could send back to you. I couldn't sign it. There's no way that I could validate where this came from. So that's why we got that error. But let's see what happens when we do get that record back. Let's go to packet 3. Now again, this is not decrypted. This is right off the wire. I'm going to cloudflare.com. I'm talking to my server. I'm saying go ahead and do your little recursion, all good. If you come down to the end, accepts DNSSEC security resource records. And let's go to packet 4. Let's see what was changed here. So the response comes back. One question was asked. And this one's an interesting bit. Answer authenticated. So the answer authority portion was authenticated by the server. So my resolver was able to validate that this is true. In fact, if we come back, here's my queries, here's my answers, here's your IP addresses, and then down here, this is the record that I'm going to focus on for a little bit. So resource record signature, this is a record you can get back from your server. Time to live, data length, algorithm. So what signed it? Your key tag is basically a hash of, it's a micro hash of what the key actually was. And signer's name, cloudflare.com, and then its signature. Now I'm not going to go into the deep weeds of that signature, how that's concocted and so on. But all we want to know for now is that basically Cloudflare sent us a guarantee saying, I'm the one that actually signed this for you. This is legitimate, you can trust it, and here's your IP addresses. This will protect your cache. So if I send out this request and I ask for a DNSSEC record and I get one come back from, jimsigning.com, that's where I'm going to flag it and say, this didn't come where I think it should come from. Perhaps somebody's trying to poison my cache. This has to be signed and stamped and validated in order for me to accept it. Okay? So very simply, that's what DNSSEC is designed to do, to validate and stamp that the records that came back are legitimate and I can trust them. Now, there's a whole lot that happens in the back end, and there's a chain of trust that happens between the root, the TLD, and the authoritative name servers that resolver has to go through in order to validate that this was true and where it came from. That whole back end, you actually have it in that full recursive packet capture. If it wouldn't take me the next 45 minutes, I would actually walk you through every step in that chain and show you how that DNSSEC happens to the root signs it, and then tells us, go ahead and go to the TLD, they're legitimate, okay, they're great, they signed it, and then they pass me off to my authoritative server, and then they sign that final record. That trust chain happens on that back end, and you have that in your packets if you want to go down that rabbit hole. It's kind of fascinating. But what this means, though, just to boil that down, now my resolver, it's done all of that work for me, and when I get this come back from Cloudflare, I'm good. I know that this has been a signed and trusted record. I can trust it. There was a question over here. I'll try to answer.
I think you may have. I'm just assuming that the resolver, though, has to have some sort of list of who it can trust.
Yes. So on the back end, it goes to the root first, and the root is self-signed. So that's the only time that we take their word for it, but there's a mechanism under the hood that allows me to do that. And then from there, it signs the TLD, then it signs the authoritative name server, then that final record comes back. So the parent vouches for the child, then finally the authoritative name server comes back with the record.
Yeah, at some point, you either have to have a list that's constantly updated,
Yep.
or you have to have some sort of trust, and that would be where things will break down.
You are 100% right. So that resolver knows, that resolver has that list with the root. The root gets to self-sign it. So that's actually in the recursive PCAP that I gave you too. The only reason I hate that I gotta move, because I love this so much. I've literally spent the last few days just digging into DNSSEC and how that whole trust chain works, and it's super interesting. But for now, if you walk out of this class, there's two things I want you to know about DNSSEC. One, it is open on the web, or open on the wire. It can be seen right off the wire. It does not encrypt, okay? That's for one. For two, its purpose is to protect your cache, to sign these records, to validate where they came from, to preserve integrity and authenticity. But DNSSEC's job is not encryption, okay? Everybody good on that? If you walk out with one thing, just walk out with that. So now let's go from that resolver's cache. And now let's go into the space between the client and the resolver. I want to talk about what's happening in that space with DNS. All right? And a lot of this is happening under our noses. It's interesting, over time, I've noticed personally. Have you noticed this at all? Like, you start filtering for DNS and your UDP DNS is going away? Has anybody noticed that? If you just spend some time in your home office, home, lab, whatever, just do some captures and tell me what's going on with your DNS. It's starting to disappear on us as far as UDP 53. So where is it going? Let's look. Okay. Oh boy, I only got 13 minutes. I knew this was going to happen. I could literally make 8 hours out of this. Sorry, everybody. Okay, so let me fly. Let's talk about DoH, because I think this is the one that's really taking shape and has taken a lot of the load of what we're doing over DNS. So basically, if you would open up, please, let's go ahead and do, first let's do DNS, DoH, encrypted, okay? Let's do that. And I'm just going to take a quick spin through this one. Now, let me just take a quick walk down. Okay, so at the very top, you can see there's a couple of requests that went out. There's our DNS at this point. It's DNS over UDP, port 53. Quick side note, you see I've got an HTTPS and then an A record that I'm asking for. So the A record is your standard boilerplate, packetpioneer.com, I want an IP address for you. It comes back, and check this out, here's your address. Now, is this one signed by DNSSEC at this time? Do you see a DNSSEC record in packet 4? All right, so this is old school DNS. This is not signed. Man, I got to talk to my provider. So this is not a signed record, right? So this is just wide open. This is an example of, just standard boilerplate. There you go. But check out HTTPS. So what this is I'm sending out a record, or I'm requesting for packetpioneer.com. If my DNS server supports it, I want to see an HTTPS record come back. Now, what the heck is an HTTPS record? Well, basically what that allows me to do, and I think in this one, this one sends back a start of zone authority. So basically what this means is I don't have an HTTPS record for you, but I'm going to get to that later. Basically what this record does, an HTTPS record, is it allows the DNS server to send you back the mechanics that you need to immediately connect back to a server. And you already know the application protocol to talk to, you know the address of that server, you know some of the mechanics that you need to fire off your TLS connection. The purpose of this is to buy you time in connecting to a secure web server. Okay? So we'll actually see that in just a moment. All right, so I go to packetpioneer.com, great, wonderful, but if I come down here, check this out. This right here, Cloudflare DNS, so packet number, go ahead and join me down here at packet 120. So this is where you start to see DNS over HTTPS. So I have a TCP conversation, go to this server, send SYNACAC. I send a client hello to start off the TLS handshake. I get a server hello to come back. That establishes my encryption. And then if you come down here, you start to see, here's these smaller packets. This is what my eyes tend to look for. So 259, 189, 190. Just remember that for right now, 191, 189. So the client sends several 200-ish byte packets to the server. We turn around and then we start to see 499, 499, 499, 4099. That's kind of an interesting pattern. So right away, just my brain goes, okay, so I've got this claims to be HTTPS, but is this a client doing web to this server, or is there more under the hood? What's going on? Let's do this. I'm going to go ahead and close this. I wanted you first to see it encrypted, and then let's go ahead and open up the decrypted. So what I did is I captured the TLS session keys when I generated this, and I went ahead and I bolted them into this packet capture. So can I get a thumbs up from you if you see, basically, if you go down to packet 38, do you see finished there on your end? Packet 38 finished? Okay, that means that you're successfully decrypting it. Fuel for another conversation at SharkFest, but how you can actually capture those session keys and you can come up here to edit, inject TLS secrets. You can take the TLS secrets for the conversations that are in there and inject that into the packet capture, and that's how I can share it with you and it decrypts, okay? Fuel for another day. But let's come down to that second conversation. I'd like you to come down to packet number 120, and this is where we saw before those around 200-ish byte packets there. So we first have a TCP connection, SYN/SYN/ACK/ACK, then we see a TLS client hello, we see the server hello come back, that establishes our encryption. After that, check out packet number 133, 134, 135. All of those, this is where you start to see the mechanics of HTTP2. You notice here, over in the info there, you see it says headers 3, 5, 7, 9, 11, 13. The cool thing about HTTP2 is it can go, oh, you want to get all these DNS records, like you want this query, this query, this query, you want all these 5 queries. HTTP2 has the ability to multiplex that over one TCP connection. It has the concept of streams. So when you see that little number, headers 3, on stream 3 we have this get. On stream 5 we have this get. On stream 7 we have this get. Those are, you almost call them separate channels. Those are independent. So the server on the other side will send the corresponding response down that stream. So I can send you 100 gets, and you can start resolving those gets over the same TLS conversation, the same TCP connection. What it does is it starts to maximize our TCP connection, and we get more out of it. Imagine if we had to do all of this. What's the alternative? I've got to open up a TCP connection, SYN/SYN/ACK/ACK, TLS client hello, TLS server hello, establish encryption, do a get a response, do a get a response, do a get a response. That's HTTP 1.1. It has to put them in series like that. HTTP 2 allows us to build these streams and send it all at the same time. Okay? So, you notice this, and I actually asked Gerald about this right before doing this session. I'm like, Gerald, is there, you know, I feel really dumb sometimes. I'm like, I'm totally missing something. And then I asked Gerald, and he's like, no, you're not crazy. And I go, oh, okay. That's I felt better. If you go to packet 133, let's go to packet 133. So you have Ethernet 2, IP, TCP, transport layer security, so TLS. Sitting on top of that is HTTP 2. If we scroll down into this, this is a GET, and what we're interested in is this DNS query. So this is DoH, DNS over HTTPS. HTTPS, port 4243, is just the carrier to encrypt it. It's giving us the mechanism to send this request to our server. Now this blob that you see here, everybody see that? The AAA, BAA, all that stuff? So that's basically the hexadecimal of your DNS query. Right now, at this time, Wireshark doesn't dissect that for you. This is a DNS request. In fact, if you take packet 133, since we're decrypted, let's right-click that. We're going to go to follow. We're going to go to HTTP2 stream. If you go to HTTP2 stream, this is where you see the actual stream data. But I'm going to close this down. I want you to get back to the packets. So here's your header. So here's our get DNS query. The server comes back and says, great, okay, wonderful, but here's your actual stuff that you wanted, Chris. Go ahead and take a look at the packet 146. So this is energybillcruncher.com. That was built into Mozilla. I don't even know why it's not my... Anyway. So this is the reply that comes back for that request that was in 133. Now, at this moment, like I said, Wireshark isn't dissecting that query, but it is dissecting the response. So that's where this is kind of a fun thing to see if you see it for the first time. You've got this is Ethernet 2, IP, TCP, TLS, HTTP, and then inside HTTP 2, you have a DNS, a full DNS response. It is exactly just like it is over UDP and clear text, but now it's got all that encryption above it. While we're here, the query, I want to see, did I get an HTTPS record? One of the queries that we were asking, energybillcruncher.com, and I want an HTTPS record. So I'm going to come down here. If you go down to, snap, same thing. I don't see it there. I have it in a different conversation. Anyway, so you saw this encrypted, and it just looked like a web conversation, right? What you should look for when on your, if you capture it on your client end and you just see this web traffic and you're not really sure if it's DNS or not, what I do is I just look at those packet sizes. You have a lot of requests that are going to be around the 200-ish size. And if you see a bunch of responses that come back around this size, they're a little larger, 500, 600, it's likely you're looking at DoH, DNS over HTTPS. I'm going to bet you money your browser's doing this today. Now, let me ask you this. For the security people in the house, what do you see if all of this is not encrypted, if all this is encrypted and you're not decrypting it, what can be a challenge for you as an analyst with this? What are some things you're considering as far as monitoring your network? We're network analysts, right? So the plus here is no one can see it. Yeah. What's the trade-off? Go ahead.
Can't debug it. What's wrong with the site? Why isn't it doing something right? Can't see the data.
Can't see it. Go ahead, John.
Exfiltrating data.
Yeah. What if I have, right now, I mean, is there such thing as a DNS attack? Could something happen over a record and I'm exfilling data out a DNS messenger, or a DNS messenger could do a callback on over DNS? Absolutely. So if all of that goes behind the green lock, this has been, what you're seeing right now, the question I just asked you is why people go, I'll just leave it as it working for right now. Let's just step away from the thing because I can't see it. It's interesting, Infoblox, they put out a report on their site, I think it was the end of last year, and they said that 92% of malware has IOCs that you can detect with DNS. 92% of it. That's why for me, in my threat hunting courses, if we're looking at malware, one of the first things that we do is look at DNS. The challenge with this is now it's TCP 443. Encrypted. But I still, even if I have TCP 443 and I do my resolution, I still can at least see where that client goes to through TLS. I have a server name indicator, but even that's going away, and I'm about to show you that. There was a question here.
Yeah, so it's using 443, it's not using TCP 53.
That is correct. Now let's talk about the difference between those. Yeah, very good question. The question was, so it's using TCP 443, not TCP 53. TCP 53 is just DNS over TCP. It's wide open. But 443, DoH, the H is HTTPS. It's saying, hey, let's just borrow HTTP to carry our DNS. And we'll do it over 443. So, yep, if you look at all these ports, TCP 443, it'll walk right by your nose.
For DoT versus DoH, difference is the port, but also is the DoH also the HTTP2 versus just over TLS?
Great question. His question was, how about DoT? Let's open up the other PCAP. You guys have a DoT trace? Do you mind popping that one open? Let's go to that one next. I don't even get to talk about quick. See what happens when I get chatty. I'm just going to put this down on its face. Okay. DoT encrypted. Let's just take a look at that. So DoT encrypted. So this is literally a DoT conversation. So DNS over TLS. So what's our port number? 853. So that's what gives you the the heads up that this is DOT. We do a TCP conversation. We do our TLS handshake, exactly the same, client hello, server hello. Interesting, since client hello, if we take a look at that client hello, just a fun fact, impress your friends. You go down to TLS and you don't have a server name because you're not trying to connect to a server. You're just trying to get to the service. So that's something that I would notice. Also, if you go to the ALPN in the client hello, you can see the actual application that I'm trying to talk is DOT. So what does this mean? Well, we do our TCP, Cincinnati CAC. We do our client hello, server hello. That establishes the encryption. And then you come down here and there's no, if you decrypt this, which in this case I didn't give you the keys, it's literally a DNS query. It's DNS, seriously, like just a DNS query with nothing between it and TLS. It just sends it over. Here's my query. Here's my response. And then I'm going to use it. Now, you might have a different exposure to this than I do. For me, I've seen juries a little bit out as far as which one of these is really going to win. I think the front runner that I have personally experienced so far is that DoH is starting to lead the charge. I think in time, if we go forward a few years, I think DoQ, so DNS over quick, is going to be a front runner, especially with over the web. But right now, in-house, this is what I'm seeing more of. Now, how do you identify it, right? Well, you got your port number, 843, but also this is where a system like an Infoblox or a vendor-supported DNS provider, those systems are designed to decrypt this, inspect it, and then continue with the fulfilling that request. So that's why a lot of providers that are implementing this in-house do have the capability of inspecting it at the resolver level. They decrypt it there. Okay, so I'm going to, Roy, are you going to be mad at me if I borrow 2 more minutes? Really? Yes. Do y'all want to see where the world's really headed? I mean, you can say no. Okay. Okay, so we talked about, let me just do a quick reverse jet ski. We talked about DNSSEC, and what is the purpose of DNSSEC? Yes, integrity. Does it encrypt? No. What does it protect? Cache. Prevents from cache poisoning, spoofing. It makes sure that that record that you get back is legit. DNSSEC. Everybody good? Okay. That's not on the WCA, don't worry. Next, DoH, DNS over HTTPS. We're using the web HTTP2 protocol to actually send our DNS requests. DoT, this is actual DNS sitting on top of TCP or TLS TCP port 853. However, quick note, it's also not going to be able to multiplex gets like HTTPS can. HTTPS, you can send 20 different requests down different streams, get responses, and that's why it's starting to lead the charge. It's a bit more efficient than DoT, okay? DoT, literally, DNS sitting on top of TLS. But even if this part of DNS, let's just say I'm a passive observer and I'm watching a client, it's going out and it's resolving an address. That address comes back encrypted, so great, I can't see where you're going. But usually, I can just take a look at your TLS handshake, your TLS client hello, and I can see the server name in clear text there, right? Anybody seen that before? Let's take a quick look. Go ahead and bring up, if you would, let's bring up, okay, just go back to DoH encrypted. Let's imagine that you did not see the DNS here because it is encrypted, okay? Those 4 packets, imagine that they're not there. That's just some DoH conversation. Then I see this client go and establish a TCP conversation, and it sends this client hello. If you take a look at packet 11, and if you scroll down into packet 11 into that client hello, there's this server name indicator, SNI. And if you expand that, you can see the server name that I'm trying to talk to is packetpioneer.com. That means that my client is talking to that IP address, but not just that address. I'm telling that server, I want to talk to packetpioneer.com inside you. Because a server can host multiple websites, right? So I can go to the same IP, but specifically, this is the server I want to talk to. The web server's like, cool, Packet Pioneer's right over here. But as a passive observer, I can see that on the wire, right? So even if I missed your DNS, I can still see your SNI. That's as it is today. Great. But this is what's happening, folks. Here's what's going on. Let me show you. We're just going to cut straight to it. You see DNS, ECH, quick, decrypted. Let's just jump in there. Boy, don't wind me up about quick. I could talk about quick all the rest of the day. Would you guys be interested in that, by the way? Who's interested in quick? Yeah? Cool? Okay. All right. Maybe if there's a session to fill in. All right. So this is the decrypted version. Here's what I want you to do, and again, I'm jet skiing. This is a client connecting to a DNS resolver, sending a bunch of requests over DoH. So if you did not have the keys, this would just look like secure web traffic, okay? You wouldn't be able to see the DNS conversation. But let's go ahead and scroll, because I'm a scroller. And it's funny, all of these different requests, all I did, like legit, I was capturing the TLS session keys and I opened up Mozilla Firefox. I rarely use that browser. So I just popped it open, and this was all the stuff that it kicked out as a part of its code. It's phoning to all these different services. Anyway, what I want you to do is come down into the 4,000 range. Oh, wait, no, hang on. I am lost. I'm going to come up here. I lied. And I want you to come to 25. Oh, there it is. Okay. Go to 2517. And actually, I lied to you again. That's not the one that I want. I want 2492. In fact, I'm going to right-click that and mark it, because then it turns black. See that? It's a little easier to have it jump out at me. I'm just going to peek through here. I'm sorry, I caught this so quickly the other day, I didn't get to... Oh, yeah. Okay. That's the right one. There we go. Okay, 2488. I told you I lied to you. Go to 2488, please. And this is DNS over HTTPS, TLS, TCP, and down the chain, okay? So what I want to show you, let's expand out HTTP2. Here's our DNS response. And the request, the query that was sent was this long, scary-looking SNI, right? So encryptinsni.com. So this was the request that we sent out, and here's the answers. So we were asking for an HTTPS record. So look at all the stuff that came back. So application layer protocol. So the response that comes back, it's saying, hey, in DNS, this is not the client server hello, or client hello server hello. This is not TLS. This is DNS saying, hey, you can connect to this server. You can go straight to HTTP 3. Over quick. You can just jump to 3. You can jump to HTTP 3, or it also supports H2. Look at your service parameter. Here's the IP addresses. So here's your IPs. That server talks H3. And hey, guess what? You see this ECH record down here? That is an encrypted, I'm giving you the mechanics to encrypt your client hello. I'm telling you, hey, my public key is right here, or that server's public key is here. Go ahead and take that client hello and just encrypt that bad boy. So the next packet after this, keep in mind, this is over HTTPS. This is already encrypted. The next packet after this can be a quick packet straight to that server with an encrypted client hello. So that server name indicator, gone, encrypted. So now DNS is being used as a mechanism to give you information about your future server in advance. It's saying more than an IP address. We can do more than that. Here's your application layer stuff. Here's your encrypted ECH mechanism. Let's just get straight to encryption. That saves us a bunch of time. Because otherwise, the alternative here is that the client, instead of going straight to quick and encrypting that thing, it's first got to go, okay, TCP, SYN/SYN/ACK, TLS request, or the client requests, the server reply. Then I have to ask it, hey, can you do quick? And the server comes back, sure, here's an alternate service you can connect to. Awesome. Now I want to connect to you on quick. That all is a bunch of overhead, right? Just to get to quick takes us 27 packets or so. DNS is now being used to shortcut you there. Go straight to quick. This is the future, people. I'm already over time. I'm kind of mad about it because I could go on for the next while. I hope this was interesting to you. I hope you don't feel overwhelmed. To boil it all down, DNSSEC, protect the cache, ensure the authenticity of your DNS data, DoT, DoH, DoQ, securing the channel. Hopefully you enjoyed it. Come and find me. Appreciate you.